So I've been meaning to read this interesting paper called In Search of an Understandable Consensus Algorithm by Diego Ungaro and John Ousterhout. Sorry if I mispronounced that. From Stanford University. We'll start with the abstract. Raft is a consensus algorithm for managing a replicated log. It produces a result equivalent to multi-Paxos, and it is as efficient as Paxos. But its structure is different from Paxos. This makes Raft more understandable than Paxos and also provides a better foundation for building practical systems. In order to enhance understandability, Raft separates the key elements of consensus, such as leader election, log replication, and safety, and it enforces a stronger degree of coherency to reduce the number of states that must be considered. So just some notes here. Elements of consensus. I've written those three down, and then let's try to remember this is going to enforce a strong degree of coherency to reduce the number of states. Results from a user study demonstrate that Raft is easier for students to learn than Paxos. Raft also includes a new mechanism for changing the cluster membership. So this mechanism uses overlapping majorities to guarantee something they're calling safety. Alright, introduction. Consensus algorithms allow a collection of machines to work as a coherent group that can survive the failures of some of its members. Because of this, they play a key role in building reliable, large-scale software systems. Paxos has dominated the discussion of consensus algorithms over the last decade. Most implementations of consensus are based on Paxos or influenced by it, and Paxos has become the primary vehicle used to teach students about consensus. Unfortunately, it is quite difficult to understand, in spite of numerous attempts to make it more approachable. Furthermore, its architecture requires complex changes to support practical systems. As a result, both system builders and students struggle with Paxos. After struggling with it ourselves, we set out to find a new consensus algorithm that could provide a better foundation for system building and education. Our approach was unusual in that our primary goal was understandability. Could we define a consensus algorithm for practical systems and describe it in a way that is significantly easier to learn than Paxos? Furthermore, we wanted the algorithm to facilitate the development of intuitions that are essential for system builders. It was important not just for the algorithm to work, but for it to be obvious why it works. The result of this work is a consensus algorithm called Raft. In designing Raft, we applied specific techniques to improve understandability, including decomposition. Raft separates leader election, log replication, and safety. And we'll jump over to this column, state space reduction. So relative to Paxos, Raft reduces the degree of non-determinism and the ways servers can be inconsistent with each other. A user study with 43 students at 2 universities shows that Raft is significantly easier to understand. I'm going to skip that part. So Raft is similar in many ways to existing consensus algorithms, most notably Oki and Liskov's view-stamped replication, but it has several novel features. The first one is strong leader. Raft uses a stronger form of leadership than other consensus algorithms. For example, log entries only flow from the leader to other servers. This simplifies the management of the replicated log and makes Raft easier to understand. Okay, so I took a easy to understand note. Strong leader means leader log flow goes to other servers. Now, leader election, Raft uses randomized timers to elect leaders. This adds only a small amount of mechanism to the heartbeats already required for any consensus algorithm, while resolving conflicts simply and rapidly. All right, next is membership changes. Raft's mechanism for changing the set of servers in the cluster uses a new joint consensus approach. Now, I probably put the emphasis in the wrong area there. I was thinking of New Jack City, but no, Raft's changing of servers in the cluster uses a new joint consensus approach. where the majorities of two different configurations overlap during transitions. This allows the cluster to continue operating normally during configuration changes. We believe that Raft is superior to Paxos and other consensus algorithms, both for educational. They say this so much, I can't stand it. Like I am not even off the first page and they just repeatedly want us to know that this is easier to understand, and yet I'm understanding almost nothing about it because the only thing I understand is that they say it's easy to understand. Okay, so it is simpler and more understandable than other algorithms. It is described completely enough to meet the needs of a practical system. It has several open source implementations and is used by several companies. Its safety properties have been formally specified and proven, and its efficiency is comparable to other algorithms. The remainder of the paper introduces the replicated state machine problem, which is in section 2, discusses the strengths and weaknesses of Paxos, which is in section 3, describes our general approach to understandability. I'll probably be skipping section 4, and then presents the Raft consensus algorithm in sections 5 through 8. Okay, so starting with section 2 here, replicated state machines. Consensus algorithms typically arise in the context of replicated state machines. In this approach, state machines on a collection of servers compute identical copies of the same state and can continue operating even if some of the servers are down. Someone once described Kubernetes to me as a thing, software that plays Tetris with your resources. CPU, RAM, and I wonder if long-term storage is part of that. Well, replicated state machines are used to solve a variety of fault tolerance problems in distributed systems. For example, a large-scale system that has a single cluster leader, such as GFS, HDFS, and RAM Cloud, typically use a separate replicated state machine to manage leader election and storage configuration information that must survive leader crashes. Examples of replicated state machines include Chubby and Zookeeper. Okay, so let's jump back real quick to look at the picture. Replicated state machine architecture. The consensus algorithm manages a replicated log containing state machine commands from clients. The state machines process identical sequences of commands from the logs so that they produce the same outputs. So we have our client in step 1 going into the server to the consensus module, which 2 goes to the log. You see there's 2 over here, as there are multiple servers that this could be happening on. So here's our log, and then 3 goes up to a state machine where X is 3 and Y is 9. You can see these variables seem to have been assigned here, and then we can see it over here, which then goes back to the client, being that the client can see what those variables are. And I want to read this part again real quick. These replicated state machines are used to solve a variety of fault tolerance problems. All right, so I took notes there. These exist to address fault tolerance, and here are 3 examples where there are single cluster leaders. Replicated state machines are typically implemented using a replicated log, as shown in figure 1. Each server stores a log containing a series of commands which its state machine executes in order. Each log contains the same commands in the same order, so each state machine processes the same sequence of commands. Since the state machines are deterministic, each computes the same state and the same sequence of outputs. Keeping the replicated log consistent is the job of the consensus algorithm. Okay, so I think that is very important, and you can tell me if I've made any spelling mistakes down here. The consensus module on a server receives commands from clients and adds them to its log. It communicates with the consensus modules on other servers to ensure that every log eventually contains the same requests in the same order, even if some servers fail. Once the commands are properly replicated, each server's state machine processes them in log order, and the outputs are returned to clients. As a result, the servers appear to form a single highly reliable state machine. Consensus algorithms for practical systems typically have the following properties. They ensure safety, never returning an incorrect result under all non-Byzantine conditions, including network delays, partitions, and packet loss, duplication, and reordering. So we could talk about Byzantine fault tolerance later. For now, though, I took a safety note, basically what that means. Another property consensus algorithms have outside of safety is they are fully functional. That is available as long as any majority of the servers are operational and can communicate with each other and with clients. Thus, a typical cluster of 5 servers can tolerate the failure of any 2 servers, and servers are assumed to fail by stopping. They may later recover from state on stable storage and rejoin the cluster. Another property is they do not depend on timing to ensure consistency of the logs. So faulty clocks and extreme message delays can, at worst, cause availability problems. In the common case, a command can complete as soon as a majority of the cluster has responded to a single round of remote procedure calls. A minority of slow servers need not impact overall system performance. Okay, another property of the consensus is in the common case, a command can complete as soon as a majority of the cluster has responded to a single round of remote procedure calls. So that would be that step number 2, or maybe it'd be step number 1, a remote procedure call. So there's a procedure, there's a new value being assigned to these variables. And so what it's saying here is once a majority of the servers, a majority of the cluster has responded to that, the command is complete. If you have a few slow ones, that's not going to be a problem. So what's wrong with Paxos? And please don't tell me it's difficult to learn. Over the last 10 years, Leslie Lamport's Paxos protocol has become almost synonymous with consensus. It is the protocol most commonly taught in courses, and most implementations of consensus use it as a starting point. Paxos first defines a protocol capable of reaching agreement on a single decision, such as a single replicated log entry. Alright, I think that's a big deal. We refer to this subset as single-degree Paxos. Paxos then combines multiple instances of this protocol to facilitate a series of decisions such as a log, which is multi-Paxos. Paxos ensures both safety and liveness, and it supports changes in cluster membership. Its correctness has been proven, and it is efficient in the normal case. Unfortunately, Paxos has 2 significant drawbacks. The first drawback is that Paxos is exceptionally difficult to understand. Alright, here we go. So I might be skipping this section. Okay, what I won't skip is this part though, because it sounded good. We believe that the overall problem of reaching consensus on multiple decisions, that is, a log instead of a single entry, can be decomposed in other ways that are more direct and obvious. The second problem with Paxos is that it does not provide a good foundation for building practical implementations. One reason is that there is no widely agreed upon algorithm for multi-Paxos. Lamport's descriptions are mostly about single-degree Paxos. He sketched possible approaches to multi-Paxos, but many details are missing. There have been several attempts to flesh out and optimize Paxos, such as the ones you can find in these footnotes, but these differ from each other and from Lamport's sketches. Systems such as Chubby have implemented Paxos-like algorithms, but in most cases their details have not been published. Furthermore, the Paxos architecture is a poor one for building practical systems. This is another consequence of a single-degree decree decomposition. For example, there is little benefit to choosing a collection of log entries independently and then melding them into a sequential log. This just adds complexity. It is simpler and more efficient to design a system around a log, where new entries are appended sequentially in a constrained order. Another problem is that Paxos uses a symmetric peer-to-peer approach at its core, though it eventually suggests a weak form of leadership as a performance optimization. This makes sense in a simplified world where only one decision will be made, but few practical systems use this approach. If a series of decisions must be made, it is simpler and faster to first elect a leader and then have the leader coordinate the decision. As a result, practical systems bear little resemblance to Paxos. Each implementation begins with Paxos, discovers the difficulties in implementing it, and then develops a significantly different architecture. This is time consuming and error prone, and the difficulties of understanding Paxos exacerbate the problem. Paxos's formulation may be a good one for proving theorems about its correctness, but real implementations are so different from the Paxos that the proofs have little value. The following comment from the chubby implementers is typical. So they say there are significant gaps between the description of Paxos and real-world system. The final system will be based on an unproven protocol. Okay. So because of these problems, we conclude that Paxos does not provide a good foundation either for system building or for education. Given the importance of consensus in a large-scale software system, we decided to see if we could design an alternative with better properties, and Raft is the result of that experiment. Okay, so I'll stop the video here, and in the next one we'll talk about designing for understandability.